Okay, so at the previous lecture we discussed the Haar measure, the Haar state on a compact quantum group. Let's recall the definition. Suppose that we have a compact quantum group A. So as usual, delta denotes the co-multiplication. And suppose that H is a state on A. Then we say that H is a Haar state if the following condition holds. For each bounded linear functional omega on A, the convolution of omega and H taken in any order gives us omega of 1 multiplied by H. And in fact, it's enough to require this condition only for positive functionals. So in the special case where A is commutative, that is, A is isomorphic to the algebra of continuous functions on the compact group, so H corresponds to a positive normalized Radon measure on G, on the group. And we have seen at the previous lecture that this condition means exactly that this measure is left and right invariant. And at the end of the previous lecture, we almost proved the following theorem due to Voronovich, which states that a Haar measure exists and is unique. Well, this theorem was proved modulo the following lemma. A technical lemma, it was lemma 2 of the previous lecture. So suppose that H is a state on A, and suppose we have two positive functionals, omega and nu. So they are positive, and nu is less than or equal to omega. So the lemma states that if omega and H are related by the following equality, then the same is true for nu. Nu H equals H nu equals nu of 1 multiplied by H. So this lemma wasn't proved. This was the only missing point. So our first goal for today is to prove this lemma. Actually, we will prove only one of these two equalities. We will prove that nu H equals nu of 1H. So the second equality is proved by a similar argument. First of all, we can assume from the very beginning that omega is a state. We may assume that omega of 1 equals 1. This is equivalent to the statement that omega is a state. Because if this is not the case, then we just divide everything by omega of 1. Well, let's introduce some notation. So for each element B in A, we denote by C of B, or just by C, if the element B is fixed, the following element, one tensor H, here 1 tensor H is the respective slice map on the tensor product, applied to delta B. So this is another element in A. Now the proof of lemma 2 will be divided into several sublemmas. Sublemma 1. I claim that for each functional f on A, we have the following identity. 1 tensor fh, so here we take the convolution of f and h, applied to delta B equals 1 tensor f applied to delta C. The proof of sublemma 1 is a straightforward exercise for you. This is a straightforward calculation, which involves the co-associativity of the co-multiplication. So you simply write the explicit formula for the convolution. This is f tensor h composed with delta, and then delta appears twice. And if you interchange, change it somehow by using the co-associativity condition, you get the right-hand side. Okay, now sublemma 2. Sublemma 2 states that the equations that we want to prove, nu h equals nu of 1h, is equivalent to the following one. This holds if and only if for each A and B in our algebra, we have the following identity. Not exactly identity, but inclusion. A tensor 1 multiplied by delta C minus C tensor 1. So this element belongs to the kernel of H tensor nu. So basically, our strategy in proving lemma 2 will be to reduce, to gradually reduce this formula which we want to prove to an equivalent form, which is easier to prove. So this is sublemma 2 is the first step of our reduction. So we reduce this formula to this condition. And let's denote this condition by 1. So here is above, C is the element which is determined by B by means of this formula. Okay, let's now prove sublemma 2. Well, we want to prove this equality. Let's write it once again. First of all, we write it in the following equivalent form. We tensor it on the left by h, and we get the following. So this is an equivalent form. But in fact, to prove this, that these two functions are the same on the tensor product of A by itself, it's enough to show that they are the same on the following subspace, A tensor 1, delta of A. Well, indeed, since A is a compact quantum group, it follows from the axioms that this subspace is dense in the tensor product. Well, actually, if we if you still remember the definition was slightly different. We required that this product taken in the opposite order, that is delta of A multiplied by A tensor 1, is dense in here. But the tensor product is also a star algebra, a C-star algebra. So there is an involution, which is a ring anti-homomorphism. And so this implies that this subspace is also dense in the tensor product. Okay, so let's now apply both sides to an arbitrary element in this subspace. So we take A and B in our algebra, and let's calculate, first of all, the right-hand side of this equation. Nu of 1, H tensor H applied to A tensor 1, delta of B. So first of all, we observe that H tensor H can be written as the following composition. This is H composed with 1 tensor H. And then we apply this to the same element. Okay, now let's look at this operator, the slice map 1 tensor H. And we observe that this operator is a morphism of left A modules. So more exactly, A acts on itself by left multiplication, and A acts on the tensor product by left multiplication by element A tensor 1. And it easily follows from the definition of the slice map that it is a left A module morphism. So we can write this expression as follows. This is nu of 1 H, and since 1 tensor H is a left A module morphism, this will be A multiplied by 1 tensor H applied to delta B. Okay, but in our notation, let's look here. So this element 1 tensor H applied to delta B is our element C, defined here. So this is just the following: nu of 1 H applied to AC. And this is the same as H tensor nu applied to AC tensor 1. Okay, so let's denote this as formula 2. So this is the right-hand side of our equation, of this equation. Now let's look at the left-hand side, namely at this functional, and we apply it to the same element. Okay, take this functional, and we apply it to A tensor 1 delta B. So what is this? Again, we use the same trick. So this is H composed with 1 tensor H applied to the same element. Oh no, this is false. Of course, here now we have a new tensor H. We must replace H by the convolution. By the convolution of nu and H. Okay, now again we use the fact that this slice map is a left A module morphism. So we rewrite this as follows. This is H applied to A multiplied by 1 tensor nu convolved with H and applied to delta B. And now we use our sublemma. Sublemma 1. Namely, we use this identity. And we see that this is nothing but h applied to A multiplied by 1 tensor nu applied to delta C. This follows from sublemma 1. Okay. Okay, now we use the fact, again, we use the fact that slice maps are left module morphisms. So we write this as follows. This is H composed with 1 tensor nu applied to A1 delta C, or just H tensor nu applied to the same element. Let's denote this formula as formula 3. Okay, so let's now look at what we've just calculated. So the left-hand side of this equality is calculated here. This is formula 3. And the right-hand side is calculated here. This is formula 2. So we see that our original equality means exactly that 2 and 3 are equal to each other. So we have this. If and only if 2 equals 3. And if we now compare 2 and 3, well, we see that this is equivalent to the fact that the difference of this element and this element sits in the kernel of H tensor nu. And the difference of these two elements can be written as follows. A tensor 1 multiplied by delta C minus C tensor 1. So this element should belong to the kernel of H tensor nu. But this is exactly what we wanted to prove in sublemma 2. Okay, this completes the proof of sublemma 2. Sublemma 3 is the next reduction. Before we formulate sublemma 3, let's introduce some more notation. We denote by L H tensor nu the following subspace. So this subspace, this is a subspace in the tensor product. It consists of all elements U in the tensor product of A by itself, such that our functional H tensor nu vanishes at U tensor U star U. Well, if you still remember the GNS construction, then you probably remember that we have already met such subspaces when we discussed the GNS construction. So if we have a positive functional and H tensor nu is indeed positive, then we can always form such a subspace. So it plays an important role in the GNS construction. But what is really needed now is that the same subspace can be equivalently defined as follows. It consists of all elements U in tensor product, such that our functional H tensor nu vanishes on VU for each element V in our algebra. So when we discussed the GNS construction, we have already proved this equality by using the Cauchy-Bonnikovsky-Schwarz inequality. Okay, now, well, sublemma 3. Sublemma 3. If for each element B in our algebra, we have the following inclusion: delta C minus C tensor 1 belongs to L H tensor omega, then the conditions, the condition of sublemma 2 is satisfied. That is, then we have this property. And formula 1 holds. And this is our last reduction. So after we prove sublemma 3, so the last step in the proof will be to show that we indeed have this inclusion. So now we have to prove sublemma 3. This is very easy, actually. Let's recall that nu is less than or equal to omega by assumption. And this readily implies that LH tensor omega is contained in LH tensor nu. Well, indeed. Oh, yeah, yes, in this case. Well, because, well, this is easily, why is it so? Well, nu is less than or equal to omega. This implies that H tensor nu is less than or equal to H tensor omega. And this means that after we substitute an arbitrary positive element, we have an inequality. So we substitute U tensor U, and we see that if H tensor omega vanishes on this element, then the same is true for H tensor U. And so we have this inclusion. Okay, but now if we look here, we easily see that this subspace LH tensor nu is contained in the kernel. This is contained in the kernel of the same functional, because we can just substitute the identity of the algebra instead of V. So we have this inclusion. And now to complete the proof of sublemma 3, we just recall that LH tensor omega is not just a subspace, but this is a left ideal. Of the tensor product. The fact that this is a left ideal readily follows from this formula. So if U satisfies this condition, then say if we multiply U on the left by an arbitrary element, say W, then we get the same property. And that's it. So this completes the proof of sublemma 3. Because if indeed if this element sits in LH tensor omega, we can multiply it on the left by A tensor 1. So let's now look again at condition 1. We multiply this element on the left by A tensor 1, and we will be in the same ideal. So this element belongs to the same ideal, but we have just seen that this ideal is contained in this kernel. And so we have condition 1. Okay, now the end of the proof. End of proof of lemma 2. So now to prove lemma 2, we just verify this inclusion. So this inclusion will imply that property 1 holds, and property 1 is equivalent to our original equation. Okay, so we just check the definition. We take H tensor omega and apply it to what? We must apply it to delta C minus C tensor 1 star delta C minus C tensor 1. So we want to show that this is 0. So let's now write this more explicitly. What is this? This is, we have actually 4 summands. So the first summand is H tensor omega applied to delta of C star C. This is the first summand. The second summand minus H tensor omega applied to C star tensor 1 delta C. One more summand, again H tensor omega applied to delta of C star multiplied by C tensor 1. And finally, plus H tensor omega applied to C star C tensor 1. Okay. So for convenience, let's denote this summand by alpha 1. This will be alpha 2. This will be alpha 3. And this will be alpha 4. And the whole expression will be formula 4. Okay, so let's start with alpha 4. This is the easiest part. So what is alpha 4? Well, omega of 1 is 1, so this is just H applied to C stars. This is clear. Let's now look at part alpha 1. So what is alpha 1? So here we have the composition of H tensor omega with delta. And this composition is just the convolution by the definition of the convolution. So this is H convolved with omega and applied to C star C. But by assumption, H convolved with omega is H. Let's look at the conditions of lemma 2. Well, we have already assumed that omega of 1 is 1, so omega convolved with H is just H. So this is just H applied to C star C. In other words, alpha 1 equals alpha 4. Okay, let's now calculate alpha 2. Alpha 2, what is alpha 2? Well, let's do the following again. This is H composed with 1 tensor omega applied to C star tensor 1 delta C. Again, 1 tensor omega is a left A-module morphism, so we write this in the following way. This is C star multiplied by 1 tensor omega applied to delta C. And here we use sublemma 1 once again. So by sublemma 1, we can replace here omega by omega convolved with H, but then we must replace C by B. This is a straightforward application of sublemma 1. Okay, but now what is omega convolved with H? Again, by assumption, this is H. omega convolved with H is H. So this is one tensor H applied to delta B. And last trick, what is this? This is C, by the very definition of C. Well, let's look once again. So this is our definition of C, one tensor H applied to delta B. Okay, so again, we see that alpha 2 is H applied to C star C. So this is the same as alpha 4. And finally, what is alpha 3? Well, this is very easy because let's compare alpha 2 and alpha 3. So we see that these two elements, this one and this one, are adjoint to each other. But H tensor omega is a positive functional. And we know that each positive functional preserves the involution. So alpha 3 is the complex conjugate of alpha 2. But we already know that alpha 2 is alpha 4. And that alpha 4 is given here. And alpha 4 is obviously real because C star C is positive and H is a positive functional. So I can remove the complex conjugation here. And we see that this is alpha 4. So in summary, we see that all the four numbers are the same. Alpha 1 equals alpha 2, alpha 3, and alpha 4. And so the whole expression here is 0. This is 0. But this means exactly that our element, delta C minus C tensor 1, belongs to L H tensor omega. And this completes the proof. So let's look once again. This inclusion by sublemma 3 implies that condition 1 holds, and condition 1 by sublemma 2, condition 1 is equivalent to our initial equation. So this completes the proof. Well, a little bit tedious, but in my view, quite elementary. Just some algebraic computations. Okay, so this was the last step in the proof of the existence of the Haar state. So now we know that the Haar state on each compact quantum group exists and is unique. And this is a very useful tool. Okay, now our next goal is, and actually this will be the final goal in our course, is to discuss the corepresentation theory for compact quantum groups. Corepresentation theory is a natural quantum analog of the classical representation theory of compact topological groups. So to begin with, let's recall some basic definition of the group representation theory. So let's first of all introduce some notation. So suppose that we have two finite dimensional vector spaces, E and F. Well, we are mostly interested in the finite dimensional case because, well, this is a general phenomenon which appears both in the theory of compact groups and in the theory of compact quantum groups. So the phenomenon is that, roughly speaking, all essential information about the group or the quantum group is contained in the collection of its finite dimensional representations. So this is the main reason why we consider the finite dimensional case. So if E and F are finite dimensional vector spaces, then we denote by L of EF the vector space of all linear operators from E to F. And if F equals E, then we just write L of E. We will always topologize finite dimensional spaces in the standard way. So by definition, the standard topology on E is the topology generated by an arbitrary norm. Well, since all norms on a finite dimensional space are equivalent, this topology is unique. As usual, we denote by GL of E the set of all invertible operators on E. Invertible linear operators on E. This is an open subset of L of E. And L of E is also finite dimensional, so GL of E carries a canonical topology. And it's easily seen that GL of E becomes a topological group with respect to this topology. Now, if we have an arbitrary topological group, G, and by definition, a representation of G on E is a continuous homomorphism, a continuous group homomorphism, pi, from G to GL of E. I'd like to stress once again that here we consider the finite dimensional case only. In the infinite dimensional case, we usually use a slightly different continuity condition on pi. Right. Actually, we usually require that the action of G on E, that is the respective map from G, from the product of G and E to E, is continuous. But in the finite dimensional case, all reasonable continuity conditions on pi are equivalent. An important class of representations consists of unitary representations. So suppose now that H is a finite dimensional Hilbert space. And suppose that pi is a representation of G on H. And we say that pi is unitary if all operators pi of x are unitary. Pi of x is unitary for each x. And let's also recall the definition of a morphism between representations. So suppose we have two representations, say pi 1, on which is defined on E1, and pi 2 on E2. So these are two finite dimensional representations of G. Then by definition, a morphism an intertwining map, in Russian we say сплетающий оператор, from pi1 to pi2, by definition this is a linear map T from E1 to E2, such that T satisfies the following relation: T pi1 of x equals pi2 of x t for each x in our group. And a set of all morphisms from pi1 to pi2 will be denoted like this. Or sometimes it is convenient to denote this as follows. This is another notation for the same space. So we see that finite dimensional representations form a category. Okay, now the representation theory of compact groups can roughly be divided into three parts. First part is an elementary theory or a basic theory. Which consists of some old classical results, such as Schur's lemma, the orthogonality relations for matrix elements of reducible representations, the unitarizability of finite dimensional representations, and decomposing finite dimensional representations into irreducibles. So this is basic theory of finite dimensional representations of compact groups, which is very similar to the respective theory of representations of finite groups. The second part is usually referred to as the Peter-Weil theory. This theory deals with infinite dimensional representation mostly, and one of the basic results here states that an arbitrary unitary, not necessarily finite dimensional representation of a compact topological group is a Hilbert direct sum of finite dimensional irreducibles. So this result, in contrast to the finite dimensional case, this result is rather non-trivial. Its proof involves some functional analysis. In particular, it involves the Hilbert-Schmidt theorem. So as a corollary of this result, each unitary irreducible representation of a compact group is automatically finite dimensional. And another closely related result of this theory, which is usually also referred to as the Peter-Weil theorem, states that the algebra, the so-called algebra of representative functions, which consists of matrix elements of finite dimensional representations, is dense in the algebra of continuous functions. This is a very useful fact. And finally, part 3 of representation theory of compact groups is the so-called Tanaka-Crane theory. This theory allows us to reconstruct an arbitrary compact group from the category of its finite dimensional unitary representations. And also this theory gives us an abstract characterization of such categories. Well, it turns out that almost all results in these theories 1, 2, and 3 have quantum analogs. That is, they extend to co-representations of compact quantum groups. So the representation theory of compact quantum groups essentially consists of the same parts. Well, unfortunately, we don't have time to discuss all these results in detail. This could be a subject for a separate course. So what we're going to do, first of all, we'll discuss the basic theory of co-representations of compact quantum groups. Unfortunately, we will have to skip the Peter-Weyl theory for co-representations of compact quantum groups. The main reason is that this theory requires much more preliminaries from the theory of C-star algebras, such as, for example, the theory of Hilbert C-star modules and multiplier algebras, which is quite a long story. And if time permits, maybe I'll tell you a little bit of the Tanaka-Crane theory at the end of the next lecture. So I'll denote it by a very little plus. So this is our plan. Okay, so before we define co-representations, let's introduce some notation. Suppose that we have two unital algebras, say A and B. Then we can consider the following two embeddings, I12 and I13. So they act from tensor product of B and A to the triple tensor product B tensor A tensor A. And it's very easy to guess how they act. I12 is uniquely determined by the following rule. It takes each elementary tensor, B tensor A, to B tensor A tensor 1. And similarly, I13 takes the same element to B tensor 1 tensor A. And if I now have an arbitrary element U in the tensor product of B and A, then we denote by U12 the image of U under I12, and similarly we introduce U13. So this is the so-called Lug numbering notation. So the subscripts 1, 2, and 3 are the legs of the respective elements in the tensor product. This notation is quite standard, and it is very useful in the co-representation theory. Okay, now let's define co-representations. Suppose now that A is a compact quantum group, and suppose that E is a finite dimensional vector space. By definition, a co-representation of A delta on E is an invertible element U in the tensor product of L of E, the algebra of linear operators on E and A, such that the following condition holds. One tensor delta applied to U. So this is an element in LOV tensor A is equal to the product of U12 and U13. So these are elements of L of E tensor A tensor A. Well, actually, since delta acts to the C star tensor product of A by itself, I must put the star here. But actually, because of this equality, the right-hand side is obviously in the algebraic tensor product of L of E, A, and A. And so is the left-hand side. Okay, so this is our main definition. And just like in the case of groups, we have an important special case of unitary corepresentations. So suppose now that H is a finite dimensional Hilbert space. And let's note that in this case, the algebra of operators, L of H, is nothing but the algebra of bounded operators on H, because H is finite dimensional. So it is a C-star algebra. And hence the tensor product of L of H and A is also a C-star algebra in the canonical way. And now we give the following definition. Here we have a corepresentation U of A on H. And we say that U is unitary. If U is a unitary element of the respective C-star algebra. U is a unitary element of BOH tensor A. Okay, so now the natural question is, where does it come from? I mean, the definition of a corepresentation. Actually, of course, the definition comes from the commutative case. So let's look at the commutative case. And this is an example and a little exercise for you. So suppose that A is the algebra of continuous functions on a compact group G. So in this case, the tensor product where our corepresentations live, L of E tensor A. So this tensor product can be identified with the algebra of continuous functions on G with values in L of E. So an invertible element U in this algebra is nothing but a continuous map. A continuous map U from G to GL of E. So the invertibility of U means that the operator U of X is invertible for each X. So U acts from G to GL of E. And now let's look at our equality, which appears in the definition of a corepresentation. So first of all, we calculate the left-hand side. One tensor delta of U. Oh, sorry, before we calculate it, let's now look at the space where this element sits. So it sits in L of E tensor A tensor A. And here we have the C-star tensor product. So what is this? This can be canonically identified with the algebra of continuous functions on the product G cross G with values in L of E. So if we now take this element, this will be a continuous function of two variables with values in L of E. And explicitly, this function is given by the following formula: 1 tensor delta applied to U. So this is a function of two variables, x and y, and this is nothing but U of xy. This is an easy exercise. And on the other hand, when we calculate U12 and U13, we see that U12 of xy is just U of x, and U13 of xy is just U of y. So the equality which appears in the definition of a corepresentation, let's write it once again. So this equality means exactly that U satisfies the following condition. So we see that U is a representation, if and only if it is U is a corepresentation of C of G, if and only if it is a representation of G. So we have the following one-to-one correspondence between finite dimensional representations of G and finite dimensional corepresentations of C of G. And similarly, if we consider representations on finite dimensional Hilbert spaces, we get a bijective correspondence between finite dimensional unitary representations and finite dimensional unitary corepresentations of C of G. In fact, this picture is actually an isomorphism of categories. Of course, to make this statement precise, we have to introduce morphisms between corepresentations. But before we do it, let's look once again at the definition of a corepresentation, and let's try to interpret it in slightly different terms. This will be quite useful. So first of all, suppose that we have two finite dimensional vector spaces, E and F. Finite dimensional vector spaces and a unital algebra A. And let's observe that we have the following vector space isomorphisms. So if we take the space of linear operators from E to F and tensor it with A, then this is isomorphic to the space of linear operators from E to F tensor A. And also this space can be interpreted as the space of all A module homomorphisms from, maybe it's better to write this in the next line. So this is isomorphic to the space of all A module homomorphisms from E tensor A to F tensor A. So here we consider E tensor A and F tensor A as right A modules in a natural way. And the isomorphisms are more or less straightforward. The first isomorphism, well, if S if T tensor A sits in this space, then the respective operator from E to F tensor A takes each vector V to T of V tensor A. So this is the first isomorphism. And the second isomorphism, well, if S is an operator in here from E to F tensor A, then the respective homomorphism from E tensor A to F tensor A takes each elementary tensor V tensor A to the product S of VA. This is quite standard. In fact, the second isomorphism, I mean this isomorphism, holds for each pair of vector spaces E and F. So here E and F are not necessarily finite dimensional, and this is just this is immediate from the universal property of the tensor product. But the first isomorphism actually holds, provided that actually we can require that at least one of the spaces E and F is finite dimensional. But for arbitrary spaces, this is not the case. Okay. So if we now apply this to corepresentations, we observe that if we take an arbitrary element U in L of E tensor E, so this is the space where our corepresentations sit. So this element bijectively corresponds to a linear operator, which will be denoted by delta U from E to E tensor A. And finally, this operator corresponds bijectively to an A-module homomorphism, that's denoted by U tilde, from E tensor A to itself. To understand this better, let's look at the special case where A is the algebra of continuous functions on a compact group. Suppose that A is C of G. So in this case, L of E tensor A is the space of continuous functions from G to L of E. So, and the same for E tensor A. So E tensor A is the space of continuous functions from G to E. So in this case, delta U acts from E to the space of continuous functions from G to E, and it acts by the following formula. It takes an arbitrary vector, little v, to the function given by the following formula. So we simply apply, for each x, we simply apply the operator U of x to v. And U tilde acts from C of G e to itself. And the action is given as follows. If we apply U tilde to f, where f is a vector function from G to E, then the result will be just the pointwise application of U of x, f of x. Well, this is actually a little exercise for you, but this is quite straightforward. Okay, now now let's come back to corepresentations. So suppose that A is a compact quantum group, and in this case, I recommend you to do the following exercise. Suppose that A is a compact quantum group, And well, E is a finite dimensional vector space. And U is an element in the tensor product of L of E and A. Then U satisfies our condition, which appears in the definition of a corepresentation, if and only if the following diagram commutes. And here's the diagram. This is the map which was denoted by delta U. So once again, delta U corresponds to the element U under this isomorphism. So here we have delta U. Let's write it once again. So here we can apply the following map, one tensor delta, where delta is the co-multiplication of A. So the result will belong to the following space. And here we can apply delta U tensor 1, where 1 is the identity map of A. So I claim that, and this is an exercise for you, that this formula holds if and only if this diagram is commutative. Okay, so unfortunately, the invertibility condition of U on U, which is also a part of the definition of a corepresentation. So the invertibility condition on U doesn't seem to have a nice interpretation in terms of delta U. And in fact, this can be, we can overcome this in the case where we work with corepresentations of co-algebras with a co-unit. But compact quantum groups in general don't have co-units. And this is one of the reasons why the language of corepresentations is more convenient in the theory of compact quantum groups than the language of co-modules, which is probably well known to some of you. Anyway, this map delta U is useful sometimes when we define, for example, morphisms between corepresentations and so on. Okay, let's now introduce morphisms. Suppose that A is a compact quantum group. And suppose that we have two finite dimensional corepresentations, say U and V. Finite dimensional corepresentations of A on the vector spaces, say E and F, respectively. By definition, a morphism from U to V, or an intertwining map, is a linear operator T from E to F, such that the following equation holds. T tensor 1 composed with U tilde equals V tilde composed with T tensor 1. And this is an equation in the space of all A modular homomorphisms from E tensor A to F tensor A. Equivalently, we can define this notion as follows by using the maps delta from our previous remark. So let's look at the following picture. This is map delta U, which corresponds to the corepresentation U. Here we have a similar map delta V, which corresponds to V. Here we have T, and here we have T tensor 1. So it's easy to show, it's almost immediate from the definition, that this equality is equivalent to the statement that this diagram commutes. Okay, again, it's very easy to guess that this definition is motivated by the commutative case. Let's look at the commutative case. So again, suppose that A is the algebra of continuous functions on a compact group, G. And let's look at this diagram. So if we first apply delta U and then T tensor 1, we apply it to an arbitrary element V, little v, or maybe better, little w, because little e is very easy to, it looks very similar to the big V. So let it be W. So what is this? This is an element in here, in F tensor A. So this is a F-valued continuous function on G. And actually, this is nothing but T applied to U of X W. This is a little exercise. On the other hand, if we follow first this arrow and then this arrow, so we apply delta V T to W and then evaluate at X, the result will be V of X applied to T W. So we see that the diagram is commutative if and only if T is a morphism of the respective representations. So we conclude that T is a morphism of corepresentations, even only if it is a morphism of representations. So we see that, in particular, we see that if we look again at this diagram, that's denoted by D, we see that actually this diagram is an isomorphism of categories. Well, in conclusion, if you don't mind, I'll give you some useful source of examples of corepresentations. Indeed, so far we have only this example, which comes from the commutative case, which is not very interesting. So how about genuine examples of co-representations of compact quantum groups, of those compact quantum groups which don't come from groups, like, for example, the quantum SU2? And actually, the answer is that we have already met such examples. And to understand this, let's just write the definition of a co-representation in terms of matrices. So suppose that A is a compact quantum group, and suppose that E is a finite dimensional vector space. Let's choose basis E1 to En, basis of E. So by using this basis, we can identify the algebra of operators, L of E, with the matrix algebra, Mn. And so the tensor product of L of E and A is identified with the algebra Mn, tensor A, which is the same as the algebra of square n by n matrices with entries in A. Now it's a very easy exercise, little calculation, which shows that an element U in, well, first of all, before I formulate the exercise, let's also introduce some notation. So each element U in the tensor product bijectively corresponds to a matrix, a little u, Uij. This is a square n by n matrix with entries in A. Now a simple exercise is to show that U is a co-representation if and only if, first of all, the matrix little u is invertible. Clearly this is necessary. And now the formula which appears in the definition of a co-representation can be written in matrix terms as follows. Delta Uij is the sum over K Uik Ukj for each I and j. And this observation leads us directly to the definition of a matrix co-representation. So by definition, a matrix co-representation, respectively, unitary matrix co-representation, is an invertible matrix and in the unitary case we require this matrix to be unitary, respectively unitary matrix U and by a matrix with entries in A, satisfying the above formula. Let's denote it by star. So we see that if E is a finite dimensional vector space, after we choose a basis in E, we have a one-to-one correspondence between co-representations on U and the matrix co-representations. And similarly, if E is a finite dimensional Hilbert space and basis is orthonormal, then we get a one-to-one correspondence between unitary co-representations and unitary matrix co-representations. And here's a basic example, which we have already met some time ago. Suppose that we have a compact matrix quantum group. So by definition, this means that A is a unital C-star algebra, delta is a certain homomorphism from A to A tensor A, and U is an invertible matrix over A, which satisfies some conditions, and one of the conditions was exactly this equality. So we see that each compact matrix quantum groups comes together with a concrete matrix co-representation. U is a matrix co-representation. In particular, this is true for the quantum SU2 group. And this co-representation is usually called the so-called fundamental co-representation of A. Okay, so that's all for today. As the next lecture, we prove some useful properties of co-representations. In particular, we see that many questions about co-representations of compact quantum groups can be reduced to representations of the dual algebra of A equipped with the convolution multiplication. And next, we will show that each finite dimensional representation is finite-dimensional co-representation is unitarizable, that it is isomorphic to a unitary representation, unitary co-representation, just like in the case of compact groups. And we will eventually show that each finite-dimensional co-representation is isomorphic to a direct sum of irreducibles. And then, if time permits, I'll say just a few words about the Tanaka-Crane duality. Okay, that's all for today. Thank you.